In this video, I'm going to go over AP Precalculus topic 314, polar function graphs. So last lesson, we talked about graphing polar coordinates, and polar coordinates are in r comma theta, and we graphed them based on the angles and the distances. Now we're going to be connecting those points, and we're going to be graphing full graphs. So the first one we're going to look at is r equals 5 sine theta. So this is a typical setup for a polar curve, where you have an r equals something in terms of theta. So my inputs are going to be theta, and we'll get out corresponding r values. The first way we're going to look at this is what does the rectangular graph look like? Meaning, if I were to graph 5 sine x, what does that look like? Well, our amplitude is going to be 5, and our period is going to be 2 pi. So on my x and y axis, I've got my amplitude of 5 and a period of 2 pi, which means we can split this up into our 4 pieces. And we're graphing a sine curve. So sine starts at the midline, goes up, and cycles through our 5 points. Okay, we'll revisit this once we've gotten our polar curve to look at the relationship between them. Anytime we're graphing something new, a table of values is a great place to start. So here I'm going from 0 to 2 pi, and I've chosen to go up by pi over 6s. So you can literally just type these in. I'm not really interested in like the root 3s and stuff because graphing that's going to be tricky. So I'm going to do the decimal approximations. One way to do this is, like I said, literally just typing them in, or you can use your table feature. So I'm going to input my equation. And if I go to my table set, we're going to start at 0, and I want to go up by pi over 6. That's going to allow me to populate this chart. So then if I go to my table, these are going up by pi over 6, and I'm going to get my decimal equivalent to the nearest tenth. Now we're going to graph. So onto this, every pi over 6 is going to be every other one. So that's pi over 6, pi over 3, pi over 2, and so on. So 0 is at 0, so that's going to be right at the pole. On my first theta, pi over 6, I'm going out 1, 2, 2.5. Pi over 3, we're going 1, 2, 3, 4.3, and then 5. 2 pi over 3 is at 4.3. 5 pi over 6, we're at 1, 2.5, and then we're back to 0. 7 pi over 6 is this here, but we have a negative r value. When I have a negative r value, we plot that opposite. So that's actually the same point that we plotted earlier, and the same thing's going to keep happening. So what's happening is it's just going to keep repeating this pattern. So if I connect these dots, we get a circle. Connect the knots correctly. Okay, so how does this relate to this curve? Well, at pi over 2, we're out at 5. 0 is at 0, pi is at 0, 3 pi over 2 is at negative 5. So we can arrive at the same sort of points just from this rectangular curve. The next one I'm going to graph is 2 minus 2 cosine theta. For my rectangular graph, we're going to look at y equals 2 minus 2 cosine x. My amplitude here is 2, the coefficient of our cosine. Our period is still going to be 2 pi, but this one has a vertical shift or a midline of 2. So with a vertical shift of 2 and an amplitude of 2, my maximum value is going to be at 4, and my minimum is going to be at 0. My midline is going to be here at 2. We are graphing a negative cosine, so it's going to start at the minimum, which is 0, to the midline, to the max, to the midline, like so. Next, I'm going to fill in the chart just like I did with the last one. So I put my new equation in the calculator and generated a list of points. Again, we're going to graph. Notice all of these are positive, which corresponds to our graph here. we're looking at values, they start at 0, go up to 4, then go back down. So it has that oscillating sinusoidal thing, but let's look at how that translates on the polar plane. So 0 is again at 0. We're out just a little bit here at pi over 6. Pi over 3 is at 1. Pi over 2 is at 2. 2 pi over 3 is at 3. 5 pi over 6 is at 3.7. Then we're to 4. Then we're going to start moving closer to the origin, which is something we'll talk about in topic 315. 1, and then a little 0.3 here. Okay, so this graph, when I connect my dots, kind of looks like a shell almost. It has a little dip here, then it moves out, and then it dips back in. Okay, the last one I'm going to graph by hand here is 5 cosine 3 theta. So if I look at 5 cosine 3x, my amplitude is 5. My period is 2 pi over 3. So let's see how that turns out. Okay, so we're graphing a cosine function, which will start at the maximum. Okay, and again, we'll relate what we're going to graph on our polar curve back to this rectangular curve. This time, because this graph has a smaller period, so we're going to go closer together, I'm going up by pi over 12. So in my table of values, if I'm using my calculator, I would just change my delta step, or my step, up to pi over 12 instead of pi over 6. All right. So I have my table of values. Theta equals 0, which is this axis. We're out at 5. Okay. Each of these are going to be pi over 12. So this first one, all of them are going to have a point. So at pi over 12, we're at 3.5. Then we're at 0. At pi over 4, which is this one here, we are at negative 3.5. My next one, pi over 3, is going to be across at 5. And then we're back to 3.5, then 0. 7 pi over 12 is going to be this one. We're at 1, 2, 3.5. Next one's at 5, back to 3.5, back to 0. And then our next point's going to be at 13 pi over 12 at negative 3.5. Then we get to 11 pi over 12. Pi is going to be at negative 5, and then it's going to complete that cycle again. So if I connect the dots in the order I graphed them, we get a graph that looks like this. Kind of looks like a flower. Tying it back to here, we can get the location of these three, what we will be calling petals, from this graph here, because at 0, we have a petal. At pi over 3, negative 5, we have a petal. And then at 2 pi over 3, we have a petal. And then it just started repeating itself. The next thing I want to talk about is the symmetry that appeared in these three graphs. So my first one had a sine, and my next two had cosine. This one was symmetric to our y-axis. These two were both symmetric to the x-axis, and that's not an accident. Cosine, there's just a cosine, is always going to be symmetric to the x-axis, and sine is going to be symmetric to the y-axis. Sine is symmetric to the y-axis, and cosine is symmetric to the x-axis. This is going to be helpful because on the AP exam, you're not actually going to be graphing these things. You're going to need to be recognizing them and finding characteristics of them and identifying equations and things like that. So knowing the symmetry can be a big hit. Another thing that can be helpful, this is something you do not have to have memorized for the AP exam, nor even really know, but I find it's helpful to know what we call the classical polar curves. So we graphed some of these already, and some of these are going to be new. That last one we graphed is called a rose. So that's anything in the form r equals a cosine n theta, where n is a positive number. If it's 1, it's going to be the special case down here of being a circle. Lemniscate is kind of a wacky one. R squared equals a squared cosine 2 theta. Ends up kind of looking like an infinity symbol. A limacon, actually let's look at these two together. Limacon and cardioid are in the structure a plus b cosine theta or a plus a cosine theta. So the difference between these two, if these two numbers are the same, it's a cardioid. If these two numbers are not the same, it's a limacon. And a limacon can have a little loop, or it can be what we call dimpled, where it kind of just like goes like that. Cardioid, if you think of cardioid, you may think of, hearts. These kind of are heart-shaped graphs. Circles can be just r equals a. So like if I said r equals 2, we have everything out 2 units. Or a cosine theta or a sine theta. If it's a cosine, it's going to be symmetric to the x-axis. If it's a sine, it's going to be symmetric to the y-axis. And then we have various types of lines, but the simplest version is just theta equals something, like theta equals pi over 4 will give you something like this. I want to dig into roses a little bit more. Number 1, just because they're fun and pretty. And number 2, there's some cool patterns that come out of them. So what we're going to do is we're going to use the graphing calculator to show us some roses. Okay, so you're going to go to mode, and we're going to go to where it says function. You've been living your lives in function mode. We're going to go over to polar mode. When you hit y equals now, you have a whole bunch of r equals. Okay, so I'm going to start with just r equals 3 cosine 2 theta. So 3 cosine 2, and you're going, wow, how do I get a theta? Well, this variable button that you've been pressing for x, you probably didn't even really notice there's other stuff on this button. But if I push that button now, when I'm in polar mode, it's going to give me this third variable, which is a theta. For my window, I'm going to go from 0 to 2 pi, so you can either just type 2 pi in, because we're in radians, and I'm just going to go by like 0.1s. That's the numbers it's going to plug in. The smaller that number is, the more accurate your graph will be. It's just going to take longer to graph. For my x min and max, let's go from, I'm going to do -4 to 4 in both of them. And then I'm going to show you a cool trick to make our graph look prettier. Then we're going to go ahead and graph. Okay, well that kind of looks like a similar graph to what we did, but it's kind of squished. So I'm going to do a zoom square. We'll make ourselves a nice, pretty graph. So what we're interested in right now is the number of petals. So this one has 4 petals. So I encourage you to pause and investigate what happens if we change this number to 3, 4, 5. You may have some predictions. Let's see if they play out. Okay, if we change that number to a 3, we have 1, 2, 3 petals. If we change this number to a 4, we have 8 petals. So what's going to happen if we change it to a 5? We have 5 petals. Now at this point in class, typically everybody's graphing like 100 theta to see how many petals and what that looks like. And that's a fun thing to do. These polar graphs are really cool. There's a lot of things we can do in polar that we can't necessarily do in function mode. So feel free to play around with this. But I'm going to revisit what's their conclusion here. We had 4 petals here, then 3, then 8, then 5. The relationship is if we have an even number for that n value, then we have 2n number of petals. If n is odd, we have 1n number of petals. This again is not something that you are required to know. You could arrive at that. And what's actually happening with the 3 and the 5 is it's cycling between 0 and 2 pi. It's going through 6 different cycles. It's just they end up on top of each other. Okay, so the reason I bring these things up is from the multiple choice that we've seen, because this will be multiple choice questions. They tend to draw classical curves anyway. So if you know a little bit about them, I think that's helpful. You can arrive at it, though, without knowing that information. So here we're given a graph, and we want to match it to one of these. Now, I said before symmetry is helpful. In this case, the symmetry, it's symmetric to both the x and the y, so that's not going to eliminate anything. This does have 4 petals. So what we just discovered is that there's 4 petals. My n needs to be a 2. This one's going to have 8 petals. This one's going to have 8 petals. Another way to arrive at this, and we'll kind of look at this later, is by graphing the rectangular graph to see where the locations of these petals are. But this one's simpler, because now I'm really just deciding, is this a sine or a cosine? One great way to do that is to pick a sample spot, or a sample point, an easy one, like theta equals 0. If I plug in theta equals 0 here, sine of 0 is 0, so I'm going to get out 0, which would mean I'd have a point plotted here. This one, if I plug in a 0, cosine of 0 is 1, so I get an output of 4, which is what we have here. Another strategy would have been to graph all these rectangular graphs and try to match it. So we already know our solution, so I sketched it out real quick here. This has a period of 2 pi over 2, which is pi. So between 0 and 2 pi, we've got 2 full cycles. And these max and mins are the locations of the tips of our petals. So at 0, we had one. At pi over 2, we're at negative 4. Pi is at pi at 4. 3 pi over 2 is at negative pi. So that's another way to do this. Here's another one where we're going to match a given graph to an equation. So option 1 is to graph all of these rectangularly and match it. I'm going to go with my one little trick of symmetry in this case. This one is symmetric only to the y-axis, which means we have a sine function. And if you forget that, think about your unit circle. Your x-coordinates are cosine, your y-coordinates are sine, so cosine goes with x, sine goes with y. Same with the symmetry. Cosine is symmetric to the x-axis, sine is symmetric to the y-axis. So now we're down to these two. The only difference is a plus and a minus. So I'm going to pick a test point, and I'm going to pick pi over 2. Okay, so 0 is not going to be super helpful because we're going to get the same thing, but these ones are going to help. So if I plug in pi over 2 into each of these, sine of pi over 2 is 1. So if I have 3 plus 2, I get 5. Here I have 3 minus 2, which is going to give me 1. Well, on my graph, at pi over 2, we are at 1. If I were to plug in 3 pi over 2, we'd end up getting that 5 value. So B is our option here. Now, if we start restricting the domains, we can get parts of graphs. So these are the types of things AP is looking at, is interpreting the graph. If I restrict the domain, what's our graph look like then? So it says a portion of the graph of the polar function r equals f of theta, where f of theta equals 3 cosine 3 theta, which is a rose with 3 petals, is shown in the polar coordinate system for a is less than or equal to theta is less than or equal to b. So a and b are in between 0 and 2 pi. A is less than b. Which of the following could be A and B? Now this can be tricky because we know we can have, this is sitting here at 4 pi over 3, but could it be 2 pi or pi over 3 but negative? So what I'm going to do is graph the rectangular graph. The period is 2 pi over 3, and we have a cosine graph with an amplitude of 3. So there's our rectangular graph. Period of 2 pi over 3. We've already talked about my tips of the petals are going to be at these max and my mins. So this is one full petal, which means we're starting at 0 and ending at 0. And that was one of the reasons I wanted you to graph by hand, is to actually see that flow of how we go to the origin and then it spins around and all of that. So if I look at my option, 0 to pi over 6 is from here to here. That's only going to be half of a petal because it's going from the maximum to this middle. Pi over 6 to pi over 2. Well, in there, we're starting at 0, ending at 0, which is a good start. At pi over 3 is at negative 3. Here's pi over 3, here's negative 3. So I believe this is going to be our winner, but let's double check. Pi over 3 to 2 pi over 3, that's going to give me it'll give me 2 half petals because it's going to start at this point, draw half of one, and then another half of one. So that's not what we're looking at. And then from pi, which I have out here, to 3 pi over 2, that's not going to work either. So the rectangular graph can get us what we're looking for there. And yet another rose. So the figure shows the graph of a polar function. This one is 4 sine 2 theta. So 2 theta means we've got 4 petals. 0 is less than theta is less than 2 pi. There are 5 points labeled A, B, C, D, and E. A, B, C, D. And the origin is marked E. Starting at theta equals 0, list the order that the curve passes through the points. So I'm actually going to start with our rectangular graph again. All right, so we're graphing a sine with a period of pi, but since we're going from 0 to 2 pi, I go ahead and graphed 2 cycles. So we're just going to kind of follow what's happening here with what's happening on my polar curve. Okay, at 0, we're starting at 0. So my first point is at E. Then we go up to, this is pi over 4, is out at 4. So that's going to be point A. We know we're going to flow back to E, and then it's going to curve back here. So this point, that was A, at 3 pi over 4, we're down at negative 4. So here goes to here. So we went from A to D. We're going to go back to E, then to C, which on this one, C is going to be here, because at 5 pi over 4, we're at positive 4, which is this point. Back to E, and then we're going to finish off with B. Okay, so again, following that, we're E, A, E, D, E, C, C, E, E, B, B, E. So that's an introduction to graphing polar curves. Again, there's some great things we can do in polar, and it's just interpreting those and relating the rectangular graphs to our polar graphs.